Hi YouTube, I'm here to talk about vehicle to load on a Volvo T8, also known as a recharge plug-in hybrid electric vehicle. This is something that you cannot do from the factory. For those of you who aren't familiar with what vehicle to load means, it means extracting household current from your vehicle. So normally you plug it into your house and charge the vehicle. What we'd like to do is use the vehicle to run household type loads. In my specific case, I have a camper uh, which has an air conditioner, heater, induction cooktop, other electronic loads that I'd like to be able to run from the vehicle because the vehicle has a large 18 kilowatt battery that can be recharged from the engine, so effectively giving me unlimited power even if I'm boondocking. Other useful things you could use vehicle to load for would be in a power outage at your home, you could run essential loads such as your refrigerator or potentially your boiler. Now, there are other vehicles that you can buy that do have this function built into it. For example, the Hyundai electric vehicles have vehicle to load built into it. I understand Mazda plug-in hybrid electric vehicles have vehicle to load, along with most electric or plug-in hybrid or even hybrid pickup trucks, such as the Ford Lightning, the Rivians, the Tesla Cybertruck, among others, I'm sure. This is an outline, cutaway, essentially top-down view of the basic structure of the Volvo T8 or recharge system and how it works. And we need to understand how it works in order to understand how we could potentially get power out of it when it's not designed to do that for us, how we can hack the system. So if you can see my cursor here, the basic structure is a normal gas motor in the front. So this is the front wheels, front motor with 8-speed transmission. It's essentially a front wheel drive gas car and then a rear wheel drive electric car all put into one. And in between is the high voltage battery. So uh, the high voltage battery uh, is shared between the two, uh, but mostly it provides the functions of driving the rear wheels, providing the air conditioning, and also supplying the 12-volt electric loads of the car through a 12-volt converter. So let's go through that in a little more detail. The, the front engine does not have an alternator, and it does not have a starter. Instead, it has a starter generator, which you can't see here, but it's a small pancake motor generator that's right on the crankshaft of the motor. And it is driven three-phase AC through an inverter module. This is the inverter module right here. And the inverter module is plugged into the battery, the high voltage battery. The inverter module also contains the DC to DC converter that supplies 12 volts DC for the rest of the car, and we'll talk about that in a minute. In the back, we have another much more powerful motor generator that powers the rear wheels, 150 horsepower, and that receives its three-phase AC through this unit, which is another inverter module that takes 12 volts, not 12 volts, takes 400 volts nominal high voltage DC and converts it into necessary AC to turn the motor or to generate power if you're doing regenerative braking. This module right here is the charger. So when you plug the car into the wall, it converts that 120 or 240 volts AC into the high voltage DC to charge the battery. Other high voltage components, there is a high voltage AC compressor, which you can't see, it's under here. And not shown in this cutaway, there's a high voltage coolant heater that sits in the rear well behind the right wheel. So this diagram also doesn't show the 12-volt system, which we're going to talk about in a second as well. but there is a 12-volt battery that sits on a shelf in the back here, and that provides your, most of the functions of the car that we didn't already talk about. So the computers, the lights, the pumps, the power windows, the heated seats, all that stuff runs off of 12 volts. The 12-volt energy is stored in the battery here, and it's provided by this high voltage converter. There's a cable that runs from this high voltage converter to the battery in the rear. In the high voltage battery pack, we have visible on the top is a disconnect, which you can actually get to from inside the car, which would disconnect the battery for safety when you're working on it. It also contains a battery management system, which is a computer which manages the balance of all the cells and controls a high voltage contactor, which is a mechanical relay that turns the battery on, essentially energizes the battery, which supplies the power to all these high voltage components. By default, when the car is just sitting off, that contactor is open and there's no high voltage in any of these lines. That's for safety. When you turn the car on, it closes that contactor and all of these components become energized. One of the things we need to talk about first is if we want to use this for vehicle to load, the car needs to remain on, because like I said, if it shuts off, it's going to turn off all the high voltage. And by turning off all the high voltage, it's also going to turn off your source of 12 volts, which is that DC to DC converter. And you'll just be draining down your 12-volt battery until it's dead, and you're going to have a dead car. Normally, if you were to turn the car on and put it in park and get out and walk away, eventually, after about 30 minutes, the car will just turn itself off. It's going to assume that you forgot to turn it off, and it's going to do it for you. We need to stop that from happening in order to do a vehicle to load. This is the way that I have found that works to stop the car from turning itself off. So you turn the car on, you turn off the climate control, because that just uses power you don't need to use. Turn off the headlights for the same reason. Set the parking brake, it's an electronic parking brake, and then put the car in neutral, and then you can exit the car and lock it. The car is not going to turn off because it's in neutral, which is like a drive mode, so it thinks you're still driving, so it doesn't shut off, at least according to my tests. All right, the first way to get power out, which is the most obvious, which we're going to talk about, is using a 12-volt DC to 120 volts AC power inverter. You can buy these anywhere. This is the type that I have. It's a nice brand, but you can just basically buy them anywhere. And people use these with their automobiles to generate 120 volts. So why can't we do that? Well, we can. We can do this. To talk about some of the ways we could do it and also the restrictions, let's start in the front of the car. This is under the engine compartment. We're looking at that front inverter module that I talked about in the cutaway. So this is in the lower right corner of the screen is the fuse box. I've taken the cover off the fuse box. There's also a cover for this fuse here, which I've taken off. This here is the inverter module, which is liquid cooled. All these modules are liquid cooled. And this is the three-phase AC that goes down into the motor generator on the crankshaft. This is a cable that goes to the air conditioning compressor. So this module produces 12 volts or 14 volts, 14.4 volts DC, which outputs through this cable, through this 125 amp fuse, to this post, which is like a sort of a jump starting post, and then into the fuse box, and also another cable that goes to the back of the car to the battery, to the 12-volt battery. I mentioned this 125 amp fuse because this DC to DC converter doesn't have any published maximum amperage. Volvo likes to keep these things tight-lipped. So we don't really know how many amps this unit can put out, but we do know that it's got a 125 amp fuse on it. So if we pull more than 125 amps at any point after this fuse, it's going to blow that fuse. So that's important to know. The cable, this is now in the back of the car. We're looking at the battery in the back from the back, so front of the car is up, and this red cable comes in, goes under the car, comes into the battery, goes through what's called a pyro fuse, which is essentially acts like an airbag in the sense that when you have an accident, a signal triggers this to blow the fuse and shut off the 12-volt power to the car, so there's no sparks. So, and on the negative terminal, this module is a current sensor, which signals to the computer how much power is going in and out of the battery, and it uses that to monitor the state of charge of this 12-volt battery. Ignore this cable here and this cable here. I added those later, so that's not relevant really to our discussions, other than this is where you would want to hook up your 12-volt inverter. If you're hooking it up in the back, you want to hook it up here and not here, because if you hook the negative up here, oops, then you're going to be, the computer is going to detect the current going to your inverter as if it was going into the battery, which is no good. It's going to get all messed up and not know what the state of charge of this battery is, which is going to cause all kinds of problems. So it needs to be hooked up on the other side. You could just ground it to the chassis, but just as long as you don't hook it up to this terminal. Then you can hook your positive to the positive of the battery, which is under this cover. So I did this. I tested this out. I hooked my inverter up to it, turned the car on, and started drawing increasing loads, monitoring all the parameters as I increased the loads. So here's as much as I could get. This is on the left. Sorry, it's kind of hard to read. This is a DC clamp meter measuring the load coming out of that inverter module in the front of the car. And this is the amps coming out of my inverter. And this is about the most I could pull before I was at risk of blowing that fuse. So here I'm pulling 114 volts, 114 amps out of the DC to DC converter, and I'm outputting 8.29 amps out of my inverter. If I pulled any more than that, I'd be at strong risk of blowing that fuse. Now this is, if this suits your purposes, if that's enough power for what you're doing, then I think you could pretty much just stop the video here and say, well, that's how I'm going to wire it up. The problem for me is that I need to pull a little bit more than that. The air conditioning on my trailer pulls about 10 amps. This is only 8.29 amps. If I pulled 10 amps from this inverter, I would certainly blow that fuse on the DC to DC inverter or DC to DC converter, and I would have a dead car. And that fuse is $60 from Volvo. And it would leave me stranded. So this would be okay for small loads, but big loads, you're definitely going to blow that fuse. Now we say, well, what if we wired it on the other side of that fuse, sort of bypass the fuse? Well, you could do that, but now the fuse is there for a reason. Let's just put it that way. What you can do is pull DC out of it, which I have done here. Just going back to the wiring I've done. I put a wire here to a 70 amp DC circuit breaker, and then to an Anderson connector, and that way I can plug my trailer in to a DC-DC converter that pulls 50 amps and charge my trailer 50 amps from the system. And this works. I've done it. I've been using it. It works great. I can charge 50 amps from the system. The voltage is steady. Doesn't blow that 125 amp fuse. Everything's fine. But it won't run my air conditioner because it's just DC. So is there something else we can do? Well, we could try to pull 400 volts from the system, 400 volts DC from the high voltage battery directly. This is something Volvo clearly doesn't want you to do. They've gone through great pains to make it difficult to access any of this high voltage because it's deadly. And hence these cables are orange. It's to warn you that this is deadly current. And they've got all kinds of interlocks and systems designed to prevent you from doing it. But I'm the type of person who's going to do it anyway, so what's the easiest way to do it? Well, all of these connections in the back are very well hidden. All of these connections here are very well hidden. All of these connections here are very well hidden. You've got to take apart a lot of stuff just to look at these cables, never mind tap into them. There is the high voltage coolant heater, which is behind the right front wheel. That's kind of hard to get to as well, but it's a it's potential, but you got to pull the panel off behind the wheel. You got to pull the high voltage coolant heater out of its bracket. You're still getting pretty invasive. The easiest place to access the high voltage is this connector right here on the inverter module that goes to the air conditioning compressor. It's right there. You just pop the hood and there it is. You're looking right at it. So let's go look at that again. This is the connector I'm talking about. It comes right out of this inverter module, and that cable goes down to the air conditioning compressor. And it's not hard to disconnect. You could just, there's two tabs. There's a tab here and there's a similar tab on the bottom. You squeeze them and you can just pop that connector right off. And then you have access to this output if you have the right connector. Well, I did a little Googling and I figured out what kind of connector that was, and it's called a Hirschmann HPS 40-1. You can't buy these from Hirschmann. They sell them only to manufacturers, but I found on eBay that somebody had a whole bunch of these cables pre-made for some EV project, and so I bought 2 of them. Still have 39 available as of the time of this recording. It comes with a connector and about 20 feet or so of high voltage cable. Well worth it. These are very expensive connectors. This is what the end of the connector looks like. These are your plus and minus. There's a plus right there, and there's your minus. And these are low voltage interconnects. So if you put an ohm meter on these 2 connectors, you'll see that this connector and this connector have continuity between them. And the function of that is that if you pull this connector off while the system is energized, it has a circuit called the interlock circuit that detects the break in continuity. As you start to pull this, this continuity breaks before these 2 continuities break. So this continuity breaks, and that break in continuity signals to the system that to the computer that you're tampering with it, and it will shut down that high voltage contactor and de-energize the system. So it's a safety feature to prevent you from being exposed to the high voltage or for arcing to occur. So that's just something to be aware of. But these cables that I purchased already have that function wired up correctly. Here's something I found on AliExpress. It's a 8,000 watt, 8 kilowatt inverter board that will input 320 volts to 420 volts, which is approximately the range of our battery pack, and output 110 volts or 220 volts household current. Well, that's what we need, so I ordered one of those, and it arrived. It arrived set to 220 volts at 50 hertz. In order to switch it to 60 hertz, you have to unsolder this tiny little resistor, which is like a grain of rice, maybe smaller, and then off of R6 and then put it on R5, which was a pain, but I did it. You don't necessarily have to do that if you're happy with 50 hertz. Most appliances will run fine on 50 hertz, but they will potentially not operate at correct efficiency, or some things will refuse to run altogether. I mean, like microwaves sometimes will refuse to run on 50 hertz. But I switched it to 60 hertz like you're supposed to. Also, you could set it to 110 volts. Just going back, there's a potentiometer. I can't see it in this, but there's a small potentiometer which you just adjust to set the voltage down to 120. And incidentally, this is rated 8,000 watts at 220 volts. If you dial it down to 110 volts, it's only rated for half the capacity, so 4,000 watts, which is still plenty for what I'm doing. One of the things you need to be aware of is that this inverter module has capacitors on. I'll go back here. These capacitors here on the input side, these are 180 microfarads each times 4. So it's 740 microfarads at 450 volts rated capacitors. If you hook that up to an enormous battery pack and flip the switch, there's going to be a huge inrush of current into these capacitors. Massive inrush of current into these capacitors that can be potentially damaging to the capacitors themselves and anything else that's in the way. So it's necessary or a good idea to limit that inrush current so you don't get 1,000 amps when you flip the switch. It can damage your switch, it can cause pitting, arcing, all kinds of problems. So I purchased an inrush current limiter rated for 15 amps at 10 ohms. So if 10 ohms is nominal at 25 degrees Celsius, they're basically negative temperature coefficient resistors. As they get warm, the resistance drops. So they help to block the inrush current when they're cold, and then they get hot from the current flowing through them, and they conduct electricity a lot better, so that when you're pulling 15 amps through it, its resistance is only zero point 0.1 ohms. They still dissipate a fair amount of heat. This thing, it's not a super efficient way to do this, but it's in the general scheme of things, it's a simple and cheap and reliable way to protect your system. This will probably output about 25 watts when it's running. It puts out a little bit of heat, but it's fine. I 3D printed a case. This is my 3D model for a case and the lid, and there it is assembled. I put this is a 1000 volt rated circuit breaker, DC rated circuit breaker, 10 amps. 10 amps at 400 volts, about 4 kilowatts. I'm certainly not going to pull more than 4 kilowatts. I could have used an RV plug instead of a 20 amp GFCI plug. 30 amp RV plug would have been appropriate in my case, but this gives me more flexibility to plug whatever I want into it, and I don't plan on pulling more than 20 amps from my RV. Like I said, my air conditioner pulls about 10 amps, and that's about all I really need. These are PC case fans, and I don't have video of it operating, but it operates. I tested this and plugged it in. It's very easy to do. The basic idea is you turn the car off, pop the hood, wait a couple of minutes for the car to fully shut down. You'll hear a click and the car will be fully shut down. That tells you that the high voltage is turned off. And then you can just pop that connector off under the hood and pop this connector on in its place and turn the car back on. And this comes to life and has power, and I've run it and for quite a while, for several hours at a time, with no ill effects. Hasn't thrown any codes on the car. I was initially a little bit worried about disconnecting the air conditioning compressor. In theory, the air conditioning compressor could be used to cool the battery, but I haven't seen it, and it hasn't thrown any codes, like I said, so it's been fine. The reason I brought two cables. This was because I was going to make a Y cable if I needed to, so that I could direct power to the air conditioning compressor at the same time that I pulled power into my inverter, but I didn't need to do that, seemingly, so I've just left it alone with a one connector. The car seems to account for the power being drawn out of it. You can see the battery level drop as you're using it, and if it gets to 0, then the engine will start and keep everything running. So it's just automatic. Car acts as if it was designed to have this there. Essentially, there's no problems that I could see. This is not a detailed assembly instruction. I kind of figured that if you're the type of person who wants to is willing to undertake this kind of project, you should be familiar enough with some of the basics of working with wiring electricity that that you're not going to get yourself into trouble. If I made a step-by-step, then I'm kind of a little worried that people who kind of have no business doing this would do it. But if you're familiar enough with electricity and with wiring and with high voltage, this gives sort of an overall view that it is possible and how it can be done. I'll put a link down below to my 3D printed files for this case. Obviously it only fits this particular inverter, but if you did buy that particular inverter, then it might be helpful to have that case. Anyway, I hope you all find this useful, and I'd say like and subscribe, but I'm not in this for YouTube money, so I don't really care. Don't like, don't subscribe.